good afternoon. First, I thank Dan, I thank Cornell University for inviting me to this school lecture. So my talk is new direction in spintronics, kernel spin orbitronics. In fact, we have heard about spin orbitronics several times this morning already. This is a really interesting new direction of spintronics. So I can introduce spin orbit electronics in this way. Okay. In classical spintronics, say GMR, classical STT experiments, spin polarized current or pure spin current are created or detected by putting on the road of the electron magnetic materials and using the exchange interaction between the spin of the conduction electron and the local spins. Now it begins to, and this can be also used to revert the magnetization in SCT experiments, classical SCT experiments. And now it begins to be known, and the group of Bob and Dan and Kerman have been one of the pioneers in this field, that spin polarized current can be also created or detected by using in non-magnetic material the spin-orbit interaction, and this parasitic correction to the quantum mechanical equations. And for example, by using the spin-Hall effect in material with large spin-orbit coupling, or the spin momentum locking in at hash-bar interfaces between two different materials. One of them at least has a large spin-orbit coupling, or the similar effect of spin momentum locking at the surface or interface of topological insulator. We have seen an example this morning. Also similar effects on graphene when used by proximity effect, a strong spin-orbit interaction inside the graphene. And this can be used, but in fact, it can be interesting to develop a spintronic device without magnetic material and without a magnetic field needed to reorient the magnetic material and to control the polarization. But magnetic material remain anyhow essential for the non-volatile storage of information, or to go and store the information. But even for this application, for this operation, spin-orbit interaction can be used to create new type of magnetic configurations that are interesting to store the information. For example, to create magnetic skirmions or to create a chiral domain wall, Yaroshinsky-Moria domain wall. And sometimes also several spin-orbit effects can be combined to create an interesting effect. For example, in this simulation, you can see the motion of a skirmion induced by spin-orbit coupling by the spin-Hall effect. And so there are several examples of this combination of two spin-orbit effects. So today I will review some of these spin-orbit effects. I will begin by the magnetic skirmions and the potential for application. Then I will proceed to a second category of effect, spin-Hall effect, hash-bar addition effect, application, and we will describe the application to domain wall motion. And if some time left, I will say a few words of what can be done on graphene by introducing locally some spin-orbit effect by proximity effect. So I begin with skirmions. On the top of the screen, you can see typical images of skirmions supposed to be in a layer, in a thin layer with vertical magnetization. So this is a sort of soliton, so local winding of the spin configuration that you can see two examples here, and these windings are topologically protected, that you cannot unwind. They can be unwinded by simply a continuous rotation of the magnetization. You have to cross a topological barrier to change, for example, this configuration into a fermented configuration. If one look more carefully to the configuration, you can see the spin are up on this side,
and then rotate in a given anti-clockwise direction to become down at the just at the center, and then continue rotation in the same clockwise direction to become up. And so the rotation of 2 pi. And in fact, the same thing here, but the axis of rotation is different. And so that all, in fact, if you consider all the direction, you can find all the possible direction on this sphere. And mathematically, this Skyrmion can be characterized by the Skyrmion number. You can see the mathematical expression. So this configuration, this has been introduced, this type of topological protected state has been introduced first by Mr. Skyrm a long time ago for a problem of fundamental particle. Then the mechanism of this in most systems, not in all the systems, the mechanism is the existence of Dirichlet-Moreau interaction, either when the lattice has no center of symmetry by inversion, non-centrosymmetric lattices. You can see example of Lorentz microscopy image in this compound, or they can be obtained also when the symmetry breaking is due to the existence of an interface, when the absence of symmetry by inversion is due to the interface. For example, this image constructed from SPSTM experiments for one monolayer of iron on iridium 111. Dirichlet-Moreau interaction, okay, and another interesting property, this Skyrmion can be moved by relatively small electrical currents. You can see a simulation of motion by the spinel effect of Skyrmions, and the property that this current can be very small. So Dirichlet-Moreau interaction, this type of interaction, you can see, and for example, if D12 is the Dirichlet-Moreau vector is along the axis between the two spins, you can lower the energy by rotating the spin like in a block wall, and on the contrary, and this gives rise to this type of structure. Or if D12 is perpendicular to the initial direction, then you decrease the energy by rotating like in a block wall, and this gives this sort of direction. So I know better these situations because this brings me back to my work a long time ago, more than 20 years ago, on the Dirichlet-Moreau interaction induced by EV metals impurity in copper manganese, in spin glass. So the problem was to explain why in copper manganese the magnetic anisotropy is enhanced by a huge factor by introducing a few percent of magnetic impurity like platinum typically. And the idea was to find the calculation that I worked out with Peter Levy is to show that when there are two spins in a metallic system, there is not only the exchange interaction, but when you calculate the RKKY interaction in the presence of an atom, platinum with large spin-orbit coupling, resonance with spin-orbit split states, you introduce automatically a Dirichlet-Moreau terms that can be important, you can calculate it, and can be, say, 20-30% of the RKKY exchange interaction. And there was a reasonable agreement to explain the efficiency of different type of impurity in copper manganese. And a few years later, I extended this picture to the situation of the interface of a bilayer, a layer with large spin-orbit coupling, and say a cobalt layer, platinum and cobalt. And then if you apply this picture to this sort of triangle, you obtain this D12, Dirichlet-Moreau vector. And because there is no symmetric triangle, because there is no platinum above the interface, there is no compensation, symmetry breaking, of this Dirichlet. It remains a large, the symmetry breaking gives a large Dirichlet-Moreau interaction, not only for this first layer, but suppose that platinum has also some induced magnetic moment, you have also the same difference of symmetry between these two triangles, and you can also have large Dielectric-Schimmer interaction for these platinum atoms. Okay, and this interface Dielectric-Schimmer interaction are known to now today, recently, to generate different type of effects. For example, in this recent paper, it had been shown that Dielectric-Schimmer interaction at the interface with iridium and platinum induce Néel walls with different chirality, left-handed and right-handed, for copper nickel multilayers deposited on iridium or platinum. And so this is, in fact, the Dielectric-Schimmer vector has different direction for these two interfaces. And there are other examples in the literature, in the work of the school of, in the group of Wiesenegger and Nango, and in some conditions also this Dielectric-Schimmer interaction can give rise to skirmions, as now it has been found for iron monolayer of iron palladium bilayer on iridium. Okay, so of course this is an interface effect that is progressively diluted when the thickness of the magnetic material increases. So the other interesting property that I have mentioned at the beginning is the motion by occurrence. This is a typical example of results for the compound manganese silicon. This is the velocity as a function of the field in the film in this material, and you can see that the motion can be obtained with very, very small current density compared that what is needed to move domain walls by 5 or 6 order of magnitude. This does not mean, in fact, but you can see also that the velocity are very small. In fact, if qualitatively, if you compare with the motion of domain wall, we have more or less the same slopes, because the effect is again due to the spin transfer torque. But the difference is that the pinning is much stronger for domain walls than for skirmion. The skirmion motion has some flexibility, and the shape of the skirmion is also flexible, and this explains that we see simulation confirming this property, that the motion can be obtained at much smaller current density than for domain walls. Perspective for application. Okay, I am not so attracted, we are so attracted by the skirmions in non-centrosymmetric crystals. First, because generally the effects are observed below the Curie temperature, of course, and that the Curie or net temperature all the way below room temperature. So there is, at the moment, there is no perspective for application with this compound, and we are much more attracted by exploiting the possibility of coming from the Dielectric-Schimmer interaction at the interfaces. For there is a multiple possible oscillation. There is no a large number of examples, but there is many interesting to explore the multiple possible association of magnetic metal and metal with large spinobit coupling in bilayer or multilayer. Multilayer means that if you have to combine, you have to put on both sides, on the two sides of a ferromagnetic layer, two materials with large spinobit coupling, and having, in fact, and so you want to have the same chirality, that these two layers and use the same chirality, that in fact that they will act in opposite direction if both will be below the ferromagnetic layer. But we know now we have a lot of documentation on the different signs of the Dielectric-Schimmer interaction at various interfaces. And so what is attractive is not only the multiple possibility of association, the possibility of doing this game with several DMI active interface, playing with the thickness, with the interface anisotropy,